morning all of you. We are continuing with those coordination compounds and we are just seeing the different isomers. How we can get those different isomers in coordination compounds? That means, if we have the binding of the different ligands or the small anionic species to the particular metal ion center, we can find how they are there, particularly related to their geometry. So, the geometrical positioning of those ligands, so geometry will be related to the positioning of the different ligands. And since we are talking about the ultimate geometry of the coordination compounds, where we all know that we have a central metal ion which are bound to a number of ligand groups depending upon its coordination number. So, if we have a particular coordination number, say 4 or 6, we should be very much careful about the corresponding geometry or the available geometry which is directly related to the polyhedral, because everything related to this is a polyhedral structure, unlike our carbon chemistry we see in organic chemistry, because the most of the carbon centers which are saturated one having a tetrahedral geometry, or sometimes we get the corresponding double bond and triple bond positioning to that carbon, giving the planar arrangement. So, planar and the tetrahedral arrangement, but in case of coordination compounds, these geometries will be much more complex and there will be certain amount of distortions. So, distortions from where? The distortions are there which is available from a typical regular geometry. So, first if we know what are those regular geometries, particularly if we consider that if you have a very good square planar arrangement. So, the geometry of that particular compound will be square planar, where we have M at the center of the square plane, and then we can have the 4 ligands L, 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 L. So, the geometry is typically square planar, and whether we will get there something which will be related to that geometry is the isomers. So, the thing is coming for the corresponding geometrical isomerism. What we get, that geometrical isomerism depending upon the corresponding geometrical positioning of those ligands, giving rise to the isomers. So, how many of these isomers we can have? One such good example is a platinum compound having 2 groups of ligands, one is the chloride ion and another is the neutral ammonia molecules. So, the positioning of these basically give rise to 2 variation. One is the positioning of 2 Cl which are the adjacent or the one side of the platinum. So, it means on the right hand side, and 2 of the ammonia molecules are on the left hand side, like that of our double bonded carbon. So, if we know that if we have 2 double bonded, one double bonded carbon center is there, that means 2 carbon centers are there, then we can get 2 of them as the cis and trans isomers. Similarly, if we have 2 chlorides on one side of the platinum, that means based on the square plane on the right hand side, and other is that on the right hand side we have 1 chloride and another ammonia molecule. So, one will be termed as one particular isomer and the other will be of different type of isomers. So, as we see, like in organic chemistry, the cis trans isomerism, when we find that 2 of the Cl will be on the same side, we can extend the idea basically to the compound where we have the 2 chlorides on platinum on the right hand side. So, this particular variation we know that you can have hydrogen over here and hydrogen over here. This is a cis variety because 2 of these chloride groups are on the same side. So, this coordination compound will also be of cis type. So, the other type will be definitely a trans one, and these 2 isomers have different properties. Interestingly, if we just see when we make these compounds from the corresponding platinum salt, because the platinum we all discussed earlier, that platinum metal we can have, and from that platinum metal we can prepare the platinum chloride salt, which is PtCl2, and that PtCl2 can react further with the ammonia in a different sequences to provide either the cis isomer or the trans isomer. And when we make these compounds, and definitely these compounds are formed in the solid state, that means we can isolate these compounds in the solid form, and they have good solubility also in water or any other organic solvent. If water fails to solubilize a particular compound, we can try other organic solvents like methanol, ethanol, acetonitrile or dichloromethane to solubilize those compounds. So, first thing what we look at is the color. So, this compound, if we know and if we want to prepare, we find that this has a different color compared to the trans one. So, both of them have some yellow compound, and one is darker yellow towards orange side. So, is orange yellow in color, and another will be yellow in color. So, if we know and if we see the color in your eyes, we will find that we can immediately say which one is the cis variety and which one is the trans variety. And definitely once they have the corresponding color difference, they have also the solubility difference. So, why we are talking this solubility difference is that if we want to make the corresponding compound, as we all know that inorganic chemists are very much fascinated for analytical chemistry also, and we want to dissolve some amount of compound like we dissolve in potassium permanganate or potassium dichromate to make some standard solution in quantitative analysis. That means the titrimetric analysis. Similarly, these two compounds, if given to you, and if I ask you that how will you solubilize those compounds to get some standard solution. So, that definitely depends on the solubility of these compounds. So, solubility of these compounds in water will be important, and if we try to make some saturated compound, always we know that we report how much solubility we have for sodium chloride, how much is potassium chloride and how much is for aluminum chloride, we all know. And we have some pretty good idea about the corresponding solubility of these three chloride salts, as I just told you. One is sodium, another is potassium, and other is the aluminum. So, difference in solubility will also tell us that that much compound we can dissolve in say 100 milliliter of the corresponding solvent. And the solubility difference will definitely be there because we have the corresponding dipole moment of the overall compound, because the bond moments are different for these two compounds. Cis will have, if we know that there is a bond moment, we call that the platinum and Cl. Platinum, we know that is the positively charged species at the center, and chloride anions will be negatively charged. So, the bond dipole will be there, which is directed from platinum to Cl. Similarly, this is another bond dipole which is directed from this platinum center to the upper right hand side of the chloride unit. So, these bond dipoles will be additive in nature, and overall we have a dipole moment which is not possible for the trans variety, because the individual bond moments will be cancelled out. So, your dipole moment will be 0. And if the dipole moment can be the key factor for the solubility of these compounds in the solvents, then we can dictate that okay, we have the dipole moment which is less than, which is almost 0 to trans compounds, will have less solubility compared to the cis compound. So, color is there, solubility is there, and the dipole moment we have the corresponding thing. And the boiling point, if the compound is in the liquid state or this is on the only is available in the liquid state, they will have the difference in the boiling points, and definitely that's for the solid compound, that means like the solubility, the cis and trans compounds will have the different melting points. If we experimentally determine this, then the melting points will be also different. So, these are the very important thing or the physical characteristics what we can determine very nicely. If we have a very simple melting point determination apparatus, we can determine the melting point and we can correlate with the literature values, and we can tell the what the compound is made by us in the laboratory, if we want to make that which one is the cis compound and which one is the trans compound. So, that gives us a very good idea about the square planar compound. But what about the octahedral compound? In our last class we have discussed that we can have a situation where like this, that the platinum is of A2B2 type, This platinum is also A2B2 type, that means two types of ligands there, and for each type of ligand they are 2 in number. Similarly, if we go for octahedral, we always know that for a octahedral coordination complex we have a coordination number which is equal to 6. And if we want to have two types of ligands, so definitely one will be 3 in number, other will also be 3 in number. So, the compound will be Ma3B3 type. So, if we simply take the examples why it is A3 and why it is B3, because all of them we are considering as the monodentate ligand. So, only one point of attachment to the metal center can be established like that of our ammonia or the nitrite ion. So, similar to these two compounds which platinum we have one of them is the anionic ligand and another is the neutral donor ligand, such that we can neutralize the overall dipositive charge on the platinum center and we get a neutral compound, because it is very easy to isolate the neutral compound from the water medium also when you go for the corresponding synthesis of these compounds in water medium. Similarly, this cobalt compound also we already discussed earlier that we can have a corresponding hexaamine cobalt compound, but compared to that compound now we have 3 of these ammonia molecules will be available and other 3 are not there, which are nitrite ions, which are balancing the tripositive charge on the cobalt center. When we write the formula of this compound, immediately you can say that is a neutral compound and the coordination environment is N6, because its coordination number is 6, which is octahedral cobalt 3 center. And this can also have the facial and the meridional isomeric form, and these two forms what we discussed earlier also, that this can have a corresponding thing which is very much similar to this particular arrangement. So, what does it mean? That if we can have like your cisplatin and the transplatin, we just simply draw the octahedral geometries and how we can have the isomer. One we termed as the facial isomer and another is the meridional isomer. That I discussed earlier also, that we can draw a typical octahedron by seeing through the corresponding trigonal face. What is the trigonal face? Trigonal face is this particular face. So, this is one trigonal face and opposite to that is the other trigonal face. So, they are these two, opposition of these two. So, if we just pass one line through the center of these two faces, it will look like this. So, one will be staggered to the other. So, we have a staggered trigonal face and another one is over that, and what we see that in a particular case this particular arrangement is required, because we are looking at the corresponding octahedron through this particular one and which has a 3-fold symmetry. That means, if we rotate by 120 degree, we will reach to another equivalent configuration. So, this is the C3 axis, we call it the C3 is the symmetry axis, the fold is C3. So, this particular one, and if we just see the compound what we are talking about, which is cobalt bound to 3 ammonia and 3 nitrite groups. So, the type is definitely A3 and B3 type. So, what do? We do A, one face, because facial is related to the facial arrangement of the similar type of ligand. So, the other face, the opposite face back to the first one, which is B, 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 and this top one, this top face, this is the top face. Okay. So, this is the top face. So, top face is like this, and for the meridional arrangement, this arrangement is typically different. Is not, we are not talking about the face, but we are talking about some meridian, where this meridian is this particular part. So, this is the meridian. So, this is the meridional arrangement. So, this is B, and this is B. So, this is the corresponding meridional arrangement. So, for these monodentate ligands, so both of them are monodentate. So, for these monodentate ligand, it is very simple to have that particular type of arrangement, but what about we can have if we just go for a particular type of arrangement by the next higher order of ligand, which is the corresponding bidentate ligand. If we just go for this bidentate ligand, what will happen? Whether we can connect these A and A all these, or we can have some idea about the corresponding B's also, and whether we can have a typical arrangement where the two different types of ligands we require or not. So, basically we can have, we all know that we can have a bidentate ligand where both the donor atoms are same. This is XX type bidentate like that of our ethylene diamine, which is NH2, or we can have a XY type bidentate ligand, which is glycine, we all know, which is NH2 and C double bond O and OH, CH2 C double, which is the simplest possible amino acid, where the nitrogen is coordinating to the metal ion center and the oxygen from the carboxy end of the amino acid, which is glycine, is bound to the metal ion center. So, we can have so much complex things. So, for the very simple monodentate ligands, we can have the facial isomer and we can have the meridional isomer. So, what we will see next, that how we get the corresponding one for a arrangement where we can see that we are just fixing something where the cobalt center having one bidentate ligand and another bidentate ligand. So, two bidentate ligand and two monodentate ligand, and we are trying to get the corresponding mirror image of the same ligand. So, if we just consider that this is X and second one is also X, that means these are N-N-donal ligands, which is ethylene diamine. Say the simplest possible example is the ethylene diamine. So, that example will give us a compound where COEN2Cl2. So, what we do? We do very simple thing what we have just seen for our the corresponding cisplatin compound, that we put two of these chlorides on the right hand side. So, that was a square planar arrangement, but this is also an octahedral arrangement. So, we basically block these two positions, other two positions by bidentate ethylene diamine ligand, but we keep like your cisplatin two of these chloride groups on the right hand side. Similarly, these two chlorides, arrangement of these two chlorides are trans to each other because the Cl-CoCl bond angle is 180 degree. Here the Cl-CoCl bond angle is 90 degree. So, definitely this is the corresponding cis isomer and this is the corresponding trans isomer. But what we are seeing the corresponding mirror image, because the mirror image we all know that whether we get something where we can get the other different types of isomers. So, we bring something in our discussion that whether we get something where the corresponding mirror image is not superimposable to the original isomer or not, and sometime if it is superimposable, we have another different property related to the corresponding mirror image of that particular isomer. So, what we get, this dichloro-bis ethylene diamine cobalt 3 ion, which is COEN2Cl2 plus, we will have a positive charge because the tripositive charge on the cobalt center is balanced by two chloride ions only. So, the remaining charge on the complex cationic species is 1 positive. So, we will have these isomeric forms. So, if I ask you something related to some other form, so this is a very simple question related to that. If you have to draw, you just simply try to draw the different geometrical isomers, the positioning of these, we know this. Now, what we are doing? We are doing something where we are making much more complex, because we are putting one of the ethylene diamine, two of them are Br and two ammonia molecules are attached to it. So, we just simply see the positioning of these groups, because this is nitrogen, this is also nitrogen. So, 4 of the positions around cobalt will be occupied by the nitrogen donors of different origin. One is coming from the ammonia and other type is coming from the ethylene diamine. And apart from that, we can have the two bromide groups like the two chloride groups attached to the cobalt center. So, definitely immediately by looking at the COBr2 part, which is also a part we get right when we write the corresponding cobalt bromide salt, which is the cobaltous bromide salt. So, the positioning of these two bromide groups in the corresponding coordination compound is that we can put them as the cis position and we can put them in the trans position. So, we can have the geometrical isomers cis and trans related to these two compounds very easily. But if we see that whether there is some variation again by positioning of these ammonia with respect to the positioning of this beer, we can have another isomer, and if we can have the corresponding mirror images which are also not superimposable of the original compound, then we can have another variety of isomerism, what we call as the optical isomerism. So, like the typical definition what we know in the organic chemistry is the corresponding enantiomers. So, the isomers can give rise to us the corresponding enantiomeric forms or the enantiomers, and these enantiomers are also possible to form in case of the corresponding coordination compounds. What is that? The molecule or ion. In case of our coordination compound, occasionally we see that we are talking about not only the neutral molecule, but also we are talking about the corresponding ionic form, and those ions can be cations or anions. So, the ions we should always consider when we talk about the corresponding optical isomerism in coordination compound, but in case of organic compound we know that the organic molecule can have this type of possibility that they can exist in pair of enantiomers, and the molecule can be known as the corresponding chiral center or the having chiral center or the chiral molecule. So, we put the same compound, that means the cis variety of this bis ethylene diamine dichloride compound, and we see that the mirror image is there, and if we try to basically rotate that, the mirror image if we try to rotate, will not get the same compound which will can be superimposable to the corresponding compound what we get for the cis variety. So, if the mirror image is not superimposable to the other compound, that means the original compound, we call this particular one also the enantiomeric form with respect to the corresponding cobalt complex. So, we basically develop the chirality, because the chirality is being developed related to that of the symmetry related to that particular compound, because this is only possible for the cis variety, which is not possible for the trans variety. Because once we put these two chlorides trans to each other, and if we get the corresponding isomer, you try to practice it in a fashion that you draw the corresponding trans compound and see the corresponding image and try to superimpose the corresponding isomer to its mirror image. So, what we get over there, that is isomerism like that of our geometrical isomerism. So, another isomerism we can talk immediately about the corresponding optical isomerism. So, like geometrical isomerism, we can have the optical isomerism. So, optical isomerism, so will have some optical thing is there, that means the corresponding light, which is if it is the plane polarized light, and if the plane polarized light is passing through a solution of that compound, definitely you have to pass through the solution of the compound, and if it rotates the plane of polarization, if it rotates, then we can see that there is some optical activity of the original compound which is responsible for the rotation of the corresponding plane polarized light, and we will have the corresponding isomerism from that particular compound like that of our geometrical isomerism. So, which we get when a molecule is not superimposable on its mirror image. So, this is the very basic definition for optical isomerism. We can have two isomers, and the isomers will not be superimposable to its mirror image, and each of them will be optically active. That means, each of them will call as the enantiomers, and they will be available to rotate the plane of polarized light in opposite directions. So, if someone is rotating in one direction, the other one will definitely rotate the plane polarized light in the other direction. So, what we see that is basically this axis what we are talking about. So, this axis we are talking, and this axis is still there. So, the magnitude as well as the direction of that rotation is important. So, this particular rotation, if we consider that is a clockwise rotation, so other isomer will try to rotate this particular plane of polarized light in the opposite direction. So, that is the thing. So, the magnitude may be same, but the sign of their rotation is completely different, and that particular isomer should be leveled by that particular rotation. So, what is the corresponding optical activity? So, we call that particular compound as what is that corresponding optical activity of that particular coordination compound. So, whether the compound is optically active or not, then we will find the corresponding magnitude of that rotation of the plane polarized light, and we can express this particular. So, if sometime we report is that the sodium D line. So, if we have the corresponding sodium D lines amount of rotation, like that in your book is also that the sugar is there. Sugar is also optically active, then the magnitude of rotation is there, and during hydrolysis the sucrose is getting hydrolyzed, we all know, and the product of these two can rotate the light in two opposite directions. So, you get the corresponding thing as the inversion. So, the magnitude of this activity is related to the amount of rotation, and we report them as whether your coordination compound is also optically active or not. So, we can have a situation where we can try to rotate this in opposite directions or some other direction, but the nomenclature we introduced in the last class also, that one is the capital lambda and another is the capital delta nomenclature to this, and one is related directly to the left handed propeller arrangement of this particular arrangement if we consider simply 3 bidentate ligands. So, just now we will just see that how we can place the 3 bidentate ligands in a 3-dimensional arrangement in a octahedral center, and if it is there. So, left is matching with lambda. So, you will not be able to forget also that left is L and the lambda is also L. So, this is leveled, and the right is only the delta, the other one is also delta and is a right handed propeller twist is there. So, if we have, so when we determine some compound and its structure we determine, and viewing this particular compound through this particular the trigonal plane. So, this is the top trigonal plane and these 3 are the bottom trigonal plane, and if we look at that, this is the metal center, is the central center metal ion, and the ligands, if we see that these are the oxygen atoms, and these oxygen atoms basically coming 4 oxygen atoms. So, definitely, and these 2 are carbon. So, definitely these ligands is very well known ligand and well known molecule to us, these are the oxalate anions. So, if we have a corresponding iron oxalate compound and 3 such oxalate groups are attaching to this iron center, and overall negative charge is 3 minus, because each oxalate ion is giving 2 negative charges to the center. And since we are starting from this, so you see that on the, this is the top plane. So, the top trigonal plane, and so this is the right hand corner of this plane, and if we just see that this is going from the top to the bottom plane, and this is going from the top to bottom. The second ligand is also from top to bottom, and the third one is also from top to bottom. So, the movement of these from the top trigonal plane to the bottom trigonal plane is on the left hand direction. So, it is of the first category, that means it is having a structure which has a left handed propeller shape. So, the twist is left handed propeller twist, and we consider this as the corresponding lambda isomer. So, the lambda isomer is there, and this lambda isomer is obviously very much true. Just now life we can make a little bit complicated if we just move from this as the O-donal ligand to N-O-donal ligand, because once we have the N-O-donal ligand, and if this is a triskeleton, we see that the 3 N-O-donal ligands will give you one particular phase as N3 phase and another trigonal phase as the O3 phase. So, the possibility is there we can have the facial isomer as well as the meridional isomer. So, not only the facial and meridional isomer, when we consider the optical activity related to this particular arrangement of this propeller shaped arrangement is the lambda and the delta, we should level that particular one as the lambda and delta by looking at the corresponding positioning of those groups, that means those ligands, bidentate ligands, we level them, but we are not talking in terms of the experimentally determined activity in terms of the corresponding rotation of the plane polarized light. So, this is the other variety what we are discussing so far, where we take out the third bidentate ligand and instead of that third bidentate ligand we put these two as the chloride, but still we can retain the corresponding propeller arrangement because we can have the corresponding top trigonal plane again, and we will not consider these two groups because these two are the monodentate ligands. So, this they not contribute anything to the corresponding helicity or the propeller shape of the complex, but the propeller shape is completely determined by the corresponding positioning of these two ethylene diamine ligands on the cobalt center. So, this is again from the top to the bottom on from left to right, this is again from top to bottom from the corresponding one is in the clockwise direction. So, definitely this particular one is the delta nomenclature. So, not only the facial and meridional arrangement for unsymmetrical XY type bidentate ligand, this is also true for the corresponding cis variety. So, only the cis variety of this compound can have a delta configuration, we can have the corresponding lambda configuration as well, and we can also write the corresponding trans geometry. So, knowing the compound in its formula, so when this formula is given to you, you should be able to draw the structure and then you can frame in a such a way that you can reorient those positions of these groups depending upon its isomeric possibility. Okay. So, these are some other types of simple arrangements of these ligands. How we write basically, so these are the basic drawing basically, and how we draw the corresponding left-handed propeller and this is the right-handed propeller. So, we see this is the most simplest one and we have the corresponding solid three-dimensional bond between this metal center and the nitrogen centers. The main bond is bold from this particular one. So, bold is that means this is the top face and the dotted one is the bottom face, which is behind the corresponding plane or the screen, and the bold one is above the screen. So, we can draw this one is also within a corresponding hexagon, the benzene like hexagon also we can draw, or another one is also like this with two trigonal planes, but another one again is considering this as the corresponding hexagon, but only these are connected because these are the bidentate parts. So, three of them are bold in structure, others are not. And this is another form of this corresponding drawing, and this is the most simplest one. And in terms of this propeller drawing, so this part is bold, so this part is bold, so this part is also little bit bold. So, when you move from there, so it is basically disappearing when it goes from the top part to the bottom part of the plane. Similarly, this is also top to bottom and this is also top to bottom, giving rise to the corresponding delta isomer. So, the opposite one is obviously the corresponding delta isomeric form, and we just simply put them as in the opposite direction and the solid lines is like this. So, you see we should master enough to draw all these things. So, related to the 4 drawings of this one species and another 4 drawings. So, 4 plus 4 8 drawings, all of them are designating the delta isomer for a corresponding tristellated compound, which can be your cobalt ethylene diamine 3. So, this particular one is definitely gives us some chirality. So, we can have the chiral center. So, why this chirality is so important to us in terms of the chemistry and the fundamental application of these. So, fundamentally we see that the chirality we can generate in a particular coordination compound also, and we all know the metal centers are very important to have for any type of conversion. So, metal is there having some oxidation state, and that particular oxidation state is also important, and we can have 4 ligands or we can have 6 ligands, and we see that for a conversion, any organic compound conversion. So, we can convert a compound A, which is the organic molecule, to B, and sometimes we write simply some metal compound along with some ligand, say XX type or XY type or YY type ligand we put. That means, we can initiate something that the metal should interfere with that particular conversion from A to B, and this A can function again a ligand to that particular center, and this XY is already bound to this particular metal center like this. So, some free sites or the labile sites would be available to bind this A, and to convert it to B. And if your M is the corresponding chiral center, so if your chirality can be transmitted to the A or the B, that can also be an important factor related to the corresponding chirality of the metal ion center. So, that we get for the corresponding chirality which can be transmitted. So, all these chiral molecules can have a degree of asymmetry that makes their mirror images superimposable. As per the definition, what we see now is that if we have a typical degree of asymmetry, that means it is not a very symmetric, that of your cis compound, the cis variety. So, asymmetry is basically making this particular mirror image so non-superimposable. So, if we have asymmetry, then the corresponding mirror image we cannot superimpose on its original compound, but trans is more symmetric. So, as asymmetry we can generate, your compound or the center can be chiral, which is also true for carbon chemistry or the organic chemistry, and which is at the same time is also true for the metal ion center. So, that we can generate that chirality on the metal ion center, and that can also be transmitted for any useful purpose. One important purpose is the corresponding catalysis. So, if we have the metal center and that metal center is utilized for a catalytic conversion, just now as I told you that the metal center is being utilized for the conversion of A to B, and if we are able to make that metal ion center a chiral center, so it can induce something on the organic molecule, which can also be achieved by putting a chiral ligand. So, what is that chiral ligand? The definition of the ligand we all know. So, in the form of this corresponding synthetic organic chemistry, the term basically you just simply know is the term basically the asymmetric synthesis, which is not symmetric. So, a chiral ligand is we just put the chirality within the ligand. So, then we get the ligand in a enantiomer pure organic molecule, and once we have the ligand, and we all know that the ligand can be available to bind the corresponding metal ion center by chelation to form a corresponding catalyst, which is known as asymmetric catalyst. So, these two terms, these two keywords are important. Why we are studying all these? That one is the asymmetric synthesis due to the presence of the chiral ligand, and once it is bound to the metal ion, we are able to generate AC, which is our asymmetric catalyst. Why we are talking this asymmetric catalyst? Because they can give rise to some reaction where it can transfer its chirality to the reaction product. As I told you that it can transfer the chirality of the metal center, which is the catalyst itself, for the conversion of A to B. So, what do? We do one equivalent of catalyst, because it can repeatedly it can use. So, it has many turnover, and it can probably synthesize a large amount of chiral compound from an achiral precursor. So, the precursor A, what just now I told you that your compound A, which is being converted to B. So, A is not a chiral compound. If it is a achiral precursor, we can able to synthesize the compound B, which is the direct conversion of this corresponding catalytic reaction with the aid of a very small amount of chiral ligand. So, what is that? So, we are able to give the chiral ligand, because it is also required a very small amount, because the metal complex is being utilized as the catalyst. So, the catalytic conversion is coming from a very small use of the chiral ligand, and we can be able to generate or produce or synthesize a large amount of chiral compound through this particular technique. Okay. So, next we will just consider the corresponding equilibrium thing. So, equilibria are always very important to understand. So far we are talking about the corresponding complexation reaction of M plus L, and we have seen the situation is much more complex, because it can go in different steps to form ultimately to MLN, and this n value we know that for a simple coordination number of 2, n value can be 2, or it can go to the most accessible case is the coordination number of 6. So, having a coordination number of 2 will be getting a species which is ML2, and when we get like this we get ML6. So, this equilibria is very important to talk about. What we are talking about, that we have the M. This M can be our simple metal ion such as the cobalt 3 center or the ferric center, and we are talking about some ligands. So, ligands, what we have seen so far, that our ligand can be the simple water molecule having 2 lone pair of electrons, or the ammonia having 1 lone pair of electrons. So, this can go and bind to that particular metal ion center. And if the situation is such that when we all of them are same, that means all of them are L, we get the same type of arrangement, that means all 6 L are surrounding this particular center which is M. But if we consider that no, I will take something where we have L1 and L2 as for example, and we will take 5 of them as L1 and 1 of them as L2. So, what will be your corresponding compound? Your corresponding compound will be M L1. L1 is the level only, nothing but is the superscript. So, we call it as the superscript, and when we write, this is your subscript, which tells us that how many of these L's are present. That means 5 of them, that means L1, 5 of L1s are present to this M and is giving rise to this. So, the next step what we will do, we will just simply bring this particular species to this ML1, and we consider this as ML1 5 and L2, and this is again a octahedral compound, and you can have the 6 coordination sites around this particular metal ion center. So, what we can study, that we can study the corresponding complex equilibria which is related to that of your coordination. In the first step what we get is the ML. So, ML is forming in the first step, and in the 5th step it is forming this one, and in the last step it is attaching to something. So, all these coordination equilibria are very important to study, because in our blood we all know this is a very simple example, and this is the typical application of the corresponding coordination compounds in our life processes, which is our hemoglobin, we call as Hb, and some other species is also available which we call as the myoglobin. So, this thing is there which is there, that means ML5 species is forming. So, ML1 5 forming. So, this is one ligand atom, this is another ligand atom, and this is another ligand atom. So, to reach this particular point, that means we have 5 steps of these. So, if we just consider 5 steps, so this is your equilibrium K1. So, we can have K1, we can have K2, we can have K3, we can have K4, and we can have K5. But this is the form which we call as the deoxy form, because we know that when we go for respiration, we take dioxygen molecule. So, during respiration we are able to generate octahedral site, where this last ligand, this particular L2. So, this L2 ligand is nothing but another ligand what nature is giving us from the environment we are getting, which is molecular dioxygen. So, that is our ligand, which is a natural ligand and which is available in the biological processes for our blood. So, this particular one, so which will be therefore that another equilibrium constant when oxygen is bound to the deoxy form of hemoglobin or myoglobin is the K6. So, all these stepwise binding constants are pretty important. So, right now what we will see that how the simple thing are very important, where we can consider that the binding is this there, and the binding constant, because the equilibrium constants we know that how far we are moving from left to right is nothing else. So, if we know for any compound like this that A plus B is giving rise to C, we all know, and the physical chemists always help us in identifying this corresponding magnitude of these and all these things, how much C is forming. So, how much C is forming in this reaction medium, and which is also true that if we can have, because all these problems you solve, the corresponding solubility products and all these things related to say certain species like silver chloride, and the silver chloride is know that the precipitate which has a very low solubility, because the Ksp value is also very low we know. But if your B is ammonia and which is getting solubilized forming AgNH3 whole 2 plus, and if this particular one is moving from left to right and in a particular concentration of this ammonia and silver chloride, we should be able to concentrate our attention to determine the corresponding concentration of C or the complex species, because we know the corresponding K1 value, the formation constant value for this complexation reaction. So, everywhere for any analytical problem, any biological problem of our life processes is completely dictated by the binding constant or the formation constant of the complex species. Even we talk in terms of the corresponding solubilization of any simple salt of cobalt or any simple salt of iron with respect to in water or when we add their ammonia. So, monodentate coordinations will be there, and how it can be differed if we just go for a bidentate ligand. So, instead of having a corresponding ammonia ligand or the water ligand, we can have ethylene diamine. What will be the magnitude of corresponding K1 values, okay, or the stepwise different formation constant values. So, this basically gives us some good idea about our coordination equilibria, and this coordination equilibria can talk about and tell us about the corresponding stability of the corresponding complexes, how much stable those complexes are, because we have to move the equilibria from left to right in different steps. So, we can consider this as the corresponding stability constant. We can also consider them, we can talk the another name of this stability constant is the formation constant, because we are going to talk about the corresponding formation of the complexes and the binding also. What is that binding? Binding of the corresponding ligand to the metal ion center, and definitely is the equilibrium process, because on the left you can have the free metal ion as well as the free ligand concentration, because we are not moving towards the right hand side. If it is only above 90%, then only you get the corresponding compound in a very good yield. Otherwise, you can have the remaining metal ions and the ligands which is not in the bind form or the bound form. So, we get the formation of the complex in solution. Similarly, when the last ligand like that of our dioxygen is binding to deoxyhemoglobin or myoglobin, that also tells us something related to the corresponding stability constant or the formation constant of binding of the O2 for the formation of oxyhemoglobin or oxymyoglobin. So, related to all these cases, this is a very important thing and is a measure of the strength of interaction between the reagents that come together to form the complex, because whatever we are talking about is the complexation reaction, and in that complexation reaction we are talking about the interaction. So, initially if we have the metal ion and we are talking the corresponding coordination, even if we simply dissolve it in water, then water is interacting with the metal ion. So, we definitely have some idea about how much the interaction is and how strong the interaction is, and then lastly like that of our deoxymyoglobin and hemoglobin, how the dioxygen molecule can also interact with that particular complex. If the last coordination site is not free in our body, it cannot be free, it is only a bound form of water molecule is there. We can also talk about in terms of the corresponding replacement of those water molecules by the dioxygen. So, the relative stability of this aqua complex to that of the dioxygen complex is also important, and that all will be known by knowing the corresponding values of these formation constants. So, when a metal complex is formed, we can talk in terms of simple acid base equilibrium, because we all know, we just learned all these like simple term at the acid base equilibrium. What are those acids? Acids are our metal ions and bases are the ligands. So, simply M plus L, we can consider this as also an interaction where one is acid and another is also a base. And there will be some competition for the ligand between the metal ion and the hydrogen ion, because the protons will always be there and the protons are nothing but they are the simplest form of acids. So, those simplest form of acids will be there, particularly when we do the reaction in acid medium or the neutral water medium, protons are there. So, we have to compete this particular L. So, L can be neutral one, it can be water or it can be ammonia. We all know that when H plus is available, the water and the ammonia can bound to this water to give you the hydronium ion or the ammonium ion. So, that competition should be there, and binding of this Mn plus is also to L is also a competitive thing like that of our simple acid base equilibrium. So, if we have some labile sites which is be responsible for your deprotonation, like your carboxy end of the ligand or the phenol end of the ligand, the formula of the corresponding ligands will be HL, H2L or H3L type. There we require the deprotonation. So, we add some base externally to get this L as the charged form, that means L minus, L2 minus or L3 minus, and those L species, that means the anionic L will have some higher propensity of binding this M, and their formation constant or the binding constant would be very high if your ligands are charged. So, these two equilibria, they are competitive in nature, that means this ligand, it can be simple water or ammonia which is bind to the proton, giving rise to H3O plus or NH4 plus. Similarly, the M in a particular oxidation state of Mn plus is binding to L. If L is neutral, you can have the same charge of L M, but if it is anionic, the charge is reduced on the center, that means the corresponding M value. So, this is the step, that means the second one, that if we form this M as the ml. So, the concentration of ml what is forming on the right hand side divided by the concentration of unreacted M and unreacted L at equilibrium will give rise to some constant, and we sometimes we consider this as some beta and sometimes we consider as the K, because we have to talk about the corresponding overall formation constant. If these are forming in a stepwise manner, just now as I told you, that is K1, K2, K3 to K6, and if we can have the overall this thing, that means the multiplication or any other additive form of these individual K's, that means individual K1, K2 etc., can give rise to something which is the form of beta. So, that is there. So, you can have a stepwise constants and the overall or the cumulative constants, because in all these cases we can have a stepwise one also. So, this is that then ml is further reacting. So, once it is M is reacting in the first step with 1 L giving ml, and or you can a single step your M is reacting with 2 L giving rise to a form where we get this beta 1 2. So, beta is the corresponding constant starting from this simple M where no ligand is bound, but intermediate form was there which is ml, like that of our silver ion Ag plus is binding to ammonia, 2 ammonia groups are binding. So, in the first step one of the ammonia is binding to the silver center, and in the second step second ammonia is coming and bound to that particular silver center. So, whether these two are forming in a single step or they are in a stepwise manner, that will be dictated if we can have some idea about the corresponding beta for 2 steps. So, you write it as the beta 1 2. So, beta first step and the beta second step, and then beta 1 2 for the overall constant for the formation of this compound, where the coordination number of the metal center is 2. So, this individually we can break this beta 1 2 as the K1 and K2. So, these are the formation constant of the complexes in a step at a time. So, sometimes they can vary differently, because if the binding of the first one is very high, we get a K1 value higher than that of our K2 value. The way we are just talking about, we have the 5 steps to get the corresponding iron center for the deoxyhemoglobin or deoxymyoglobin, but the 6th is completely different, which is the binding of the O2 molecule. So, if the previous one, that means the deoxy form is very important, then it can have some good stability in the solution or in the water medium or in our body, such that that particular species is available to bind our dioxygen molecule. So, we get that in two steps, we break this in two steps as K1 and K2. So, that basically gives us some idea that how we talk about this beta 1 2 as K1 and K2, and that basically gives us the situation where beta 1 2 is nothing but your K1 and K2. So, if in a stepwise manner, if we go up to K6, we can have K1, K2, K3, K4 and K6 for this particular equilibrium process. So, this is very important, and which is also important if we go for a monodentate ligand to a bidentate one, where you find that in a complex form that some of the ligands can come out and exchange with other ligand that I just told you about the water molecules. So, these water molecules can be removed by other incoming ligand like ammonia, and we can have the corresponding K value. So, these are controlled by the typical thermodynamic factors and they relate directly to the corresponding formation constant. So, this is basically simply what we get for the corresponding formation of the hexaamine nickel 2 plus, and it is basically a corresponding 6 steps reaction, where individually each and every water molecule can be displaced or replaced by ammonia molecules to give you the corresponding hexaamine compound, or you can get this particular one by something where we use not by the ammonia molecule, but by ethylene diamine molecule. So, what will be the effect if we go for a monodentate ligand to a bidentate ligand? So, that is very important to know, and what will be the effect for this particular chelation. So, this basically is a tris chelate we get, because 3 ethylene diamine molecules will be binding to our nickel center, and that nickel center will be useful for this particular octahedral arrangement, which is similar to that of our nickel center, which is again NiN6, this is also NiN6. But in terms of the corresponding formation of these, that how we get this, that means if we have initially we talk about the corresponding replacement of the water molecule by ammonia. Now, we talk the corresponding one, that means ammonia will be replaced by the ethylene diamine. If it is possible or not, that means the binding constant of these ethylene diamine molecules will be higher, or they have the superior binding property compared to your ammonia molecule, and they will replace those ammonia molecule, because the reverse is not true. If we react it with water or water is still there, these water molecules cannot be able to replace these ammonia molecules. But ethylene diamine, if it is there, since it has a very binding constant, so some thermodynamic driving force will definitely be there when you talk this particular reaction, and it basically driven towards the right, where 6 ammonia molecules will be replaced from the coordination environment of the nickel center and will be substituted by 3 ethylene diamine molecule. And if we can able to write down the corresponding K value for this reaction, and we can individually find the corresponding parameters in terms of the thermodynamic values, that means the delta G or the delta H or T delta S and even the delta S only, then we can have some which particular contribution we can get, which is available to favor this particular reaction. So, next day we will talk from here about the corresponding driving force for this particular reaction, where the ethylene diamine is binding to that particular nickel center. Thank you very much.